Continuity in metric spaces. We know that if x d1 and y d2 are metric spaces and f is a function from x to y, then we say that f is continuous at the point x naught if either for every epsilon greater than 0 their x is delta greater than 0 such that d1 of x naught less than delta implies that d2 of their images f of x and f of x naught is less than epsilon. Or we can say that the function f is continuous at the point x naught if for every open sphere S epsilon of f of x naught centered at f of x naught, their x is an open sphere S delta x naught centered at x naught such that the image of S delta x naught is contained in S epsilon of f of x naught. Now let us consider a few properties of continuous functions in metric spaces. First theorem states that let x and y be metric spaces and f a mapping of x into y, then f is continuous at x naught if and only if xn converges to x naught implies that the sequence f of xn converges to f of x naught. For the proof, let us first assume that f is continuous at x naught. Now let us consider a sequence xn in the space x such that xn converges to x naught. Then we must show that the sequence of their images, that is sequence f of xn, will converge to f of x naught. Let S epsilon of f of x naught be an open sphere centered at f of x naught. By our assumption, as f is continuous at x naught, there will exist an open sphere S delta x naught centered at x naught such that f of S delta x naught is contained in S epsilon of f of x naught. Now we know that this sequence xn converges to x naught. So there will exist a positive integer, say m, such that xn will belong to the open sphere S delta x naught for every n greater than or equal to m, using the definition of convergence. And this implies that f of xn, the image of xn, will belong to the image of this open sphere f of S delta x naught. And from this inclusion, we can write f of S delta x naught is contained in S epsilon of f of x naught, and this is true for every n greater than or equal to m. Thus we have proved that for any epsilon greater than 0 or for any open sphere S epsilon of f of x naught centered at f of x naught, their x is a positive integer m such that f of xn belongs to the open sphere for every n greater than or equal to m. This implies that the sequence f of xn converges to f of x naught. Hence, f of xn will converge to f of x naught. Thus we have proved that whenever the sequence xn converges to x naught, the sequence f of xn will converge to f of x naught. Now to prove the converse part, we are going to assume that f is not continuous at x naught. then we show that xn converges to x naught does not imply that f of xn converges to f of x naught. Since f is not continuous at x naught, there will exist an open sphere, say S epsilon of f of x naught, such that for every delta greater than 0, f of S delta x naught is not contained in S epsilon of f of x naught. This is in fact the negation of the requirement of continuity at x naught. Let us label this relation as 1. Now, consider the sequence of open spheres S1 of x naught, S2 of 1 by 2 of x naught, S1 by 3 of x naught, and so on, S1 by n of x naught, etc. From relation 1, we can see that f of S1 by n of x naught is not contained in S epsilon of f of x naught. As we know that this is true for every delta greater than 0, so we can replace delta with 1 by n and then we will get this relation. Thus, we have proved that for any positive integer n, f of S1 by n of x naught is not contained in S epsilon of f of x naught. So, we can choose an element of this first set such that that element is not contained in this second set. That is, we can find an element, say xn, element of S1 by n of x naught, such that f of xn will definitely belong to f of S1 by n of x naught, but f of xn does not belong to S epsilon of f of x naught. That is, we have chosen f of xn as an element from this first set such that f of xn does not belong to the second open sphere. We have now obtained a sequence xn from the space X, and we can see that the sequence xn will converge to x naught because for every delta greater than 0, we can always find an integer, a positive integer m, such that 0 less than 1 by m less than epsilon less than delta, and hence S1 by m of x naught will be contained in S delta of x naught. So, for n greater than or equal to m, 1 by n will be less than or equal to 1 by m, and hence S1 by n of x naught will be contained in the open sphere with radius S1 by m, and it will be contained in S delta x naught. So, as xn belongs to S1 by n of x naught, from the very construction of the sequence xn, we know this fact, and from the above inclusion, we can say that this open sphere will be contained in S1 by m of x naught, and it will be contained in S delta x naught. So, we can see that the term xn belongs to S delta x naught, and this is true for every n greater than or equal to m. So, we can conclude that xn converges to x naught. Also, from the construction of the sequence xn, we can see that for every n element of n, f of xn does not belong to S epsilon of f of x naught. So, this means that there exists an open sphere centered at f of x naught which does not contain none of the terms of the sequence f of xn. So, this should imply that the sequence f of xn will not converge to f of x naught. Thus, we have proved that even though the sequence xn converges to x naught, f of xn does not converge to f of x naught. That is, we have proved that if f is not continuous at x naught, then xn converges to x naught does not imply that f of xn converges to f of x naught. So, the contrapositive of this conditional statement is also true. That is, we can conclude that whenever xn converges to x naught, f of xn converges to f of x naught implies that f is continuous at the point x naught. Next theorem states that let x and y be metric spaces and f a mapping from x into y, then f is continuous if and only if xn converges to x naught implies that f of xn converges to f of x naught. We know that f is continuous if and only if f is continuous at each point, and this is possible if and only if xn converges to x naught implies f of xn converges to f of x naught for every x naught using theorem A. Next theorem states that if x and y are metric spaces and f a mapping of x into y, then f is continuous if and only if f inverse of g is open in x whenever g is open in y. That is, f is continuous if and only if the inverse image of every open set is open. For the proof, let us first assume that f is continuous and consider g an open set in y. We must show that f inverse of g is open in x. If f inverse of g is empty, then obviously it is open, as empty set is open. So, we may assume that f inverse of g is non-empty. Now, we need to prove that this set f inverse of g is open. Let us consider an arbitrary point, say x naught of f inverse of g. Then obviously f of x naught will belong to g. We know that g is open in y, and since f of x naught is a point of g, there exists an open sphere centered at f of x naught contained in g. So, there exists an open sphere, say S epsilon of f of x naught, such that S epsilon of f of x naught is contained in G. Now, since f is continuous at x naught, and since we have an open sphere centered at f of x naught, here we can find a delta greater than 0 such that f of S delta x naught is contained in S epsilon of f of x naught. Let this be labeled as 3. Now, 2 and 3 together will imply that f of s delta x naught, which is contained in s epsilon f of x naught according to relation 3, and this is contained in G using relation 2. So we can conclude that f of s delta x naught is contained in G. Hence we can also say that s delta x naught is contained in the inverse image of G. Thus we have proved that for every x naught element of f inverse of G, there exists a delta greater than 0 such that s delta x naught, that is an open sphere centered at x naught, is contained in f inverse of G, and this is true for every x naught element of f inverse of G. And hence we can conclude that f inverse of G is open in the space X. So, if f is continuous, then the inverse image of every open set is open. For the converse part, assume that f inverse of G is open whenever G is open. We show that f is continuous at x for every x element of capital X. To prove this, let us consider an open sphere, say S epsilon of f of x. This open sphere is an open set and its inverse image is an open set from our assumption, and since this open sphere contains f of x, its inverse image will contain x. Thus, there will exist an open sphere centered at the point x contained in this inverse image using the definition of open sets. So, we can conclude that f is continuous at x. Since x is arbitrary, we can conclude that f is a continuous function. This completes our proof. Now let us consider the concepts of uniformly continuous function. If x and y are metric spaces with metrics d1 and d2, then a mapping f from x to y is said to be uniformly continuous if for each epsilon greater than 0, there exists delta greater than 0 such that d1 of x dash less than delta implies that d2 of f of x naught less than epsilon. Uniform continuity is essentially continuity plus the added condition that for each epsilon greater than 0, we can find a delta greater than 0 which works uniformly over the entire space. So it is clear that any uniformly continuous function is automatically continuous. Examples: f from R to R by f of x equal to 2x is uniformly continuous. Similarly, the real valued function defined on R by g of x equal to x square is continuous but not uniformly continuous. As another example, let us consider the function h defined from open interval 0, 1 to R by h of x equal to 1 by x. This function is also continuous but not uniformly continuous. Dense subset in a metric space. We say that A is a dense subset of a metric space X if the closure is equal to X. Next theorem states that let X be a metric space, let Y be a complete metric space, and let A be a dense subset, and hence it can be regarded as a dense subspace of X if F is a uniformly continuous mapping of A into Y, then F can be extended uniquely to a uniformly continuous mapping G of X into Y. For the proof, let us assume that D1 and D2 are the metrics on X and Y respectively. As a trivial case, if A is equal to X, then F is already a uniformly continuous mapping from X to Y as required. So, we now assume that A is not equal to X. We have to find an extension of F. So, we now begin by defining the extension G from X to Y. Since G is an extension of F, G and F must agree on the domain of F, that is A. So, G of X must be equal to F of X for every X element of A. Now, we have to define G of X for every X element of X minus A. Since A is a dense subset, we know that A intersects every open sphere. So, for every n element of n, if we consider the open sphere as 1 by n of X, then this open sphere will intersect A non-vacuously. So, its intersection with A will be non-empty. We are going to consider a point, say AN, from this intersection. That is, we choose AN element of S1 by n of X intersection with A for every n. Thus, we get a sequence AN. It is a sequence in A, and we can see that AN will converge to X as the distance between AN and X is less than 1 by n, and as n tends to infinity, this distance will tend to 0. So, AN will converge to X. Thus, we have obtained a convergent sequence AN. Since it is convergent, it will be Cauchy. Since F is uniformly continuous, the sequence F of AN will be Cauchy in Y. Now, as Y is a complete metric space, every Cauchy sequence in Y will be convergent. Hence, the sequence F of AN will converge to some point in Y, and we let that point to be our G of X. That is, we assume that F of AN converges to G of X. Thus, we have defined G of X for every X element of capital X. Now, to show that G is well defined, we must ensure that g of x depends only on x, not on the choice of sequence. For this, let us consider sequence Bn, another sequence in the set A, such that Bn also converges to x. Then, as Bn tends to x, we will be able to find a positive integer m1 such that the distance between Bn and x will be less than epsilon by 2 for every n greater than or equal to m. Similarly, as An converges to x, there will exist some m2 element of n such that d of An x less than epsilon by 2 for all n greater than or equal to m2. And if we let m to be the maximum of these two numbers m1 and m2, then for every n greater than or equal to m, d of An x will be less than epsilon by 2 and d of Bn x will be less than epsilon by 2, so that the distance between An and Bn is less than or equal to d of An x plus the distance between Bn and x, which will be less than epsilon by 2 plus epsilon by 2. So the distance between An and Bn is less than epsilon for all n greater than or equal to m. Hence we can see that the distance between An and Bn will tend to 0. By the uniform continuity of f, the distance between f of An and f of Bn will also tend to 0. And this implies that f of Bn will also converge to the same limit point as that of f of A. That is, f of Bn will converge to x. Thus we have proved that the function g is well defined. Now we must show that g is uniformly continuous. For this, let us consider an epsilon greater than 0. Now using the uniform continuity of f, we have delta greater than 0 such that the distance between two points A and A dash less than delta will imply that the distance between their images f of A and f of A dash will be less than epsilon. Prove that g is uniformly continuous. We are going to show that distance between x and x dash less than delta will imply that the distance between g of x and g of x dash will be less than or equal to epsilon. For this, let us consider x and x dash from the space x. Then there exists two sequences An and Bn in A such that An converges to x and Bn converges to x dash. By triangle inequality, we have the distance between An and Bn less than or equal to the distance between An and x plus distance between x and x dash plus distance between x dash and Bn. Here we know that as An converges to x, the distance between An and x will tend to 0 as n tends to infinity. Similarly, since Bn converges to x dash, the distance between Bn and x dash will also tend to 0. So the right side of this inequality will be tending to 0 plus delta plus 0. So we have the distance between an and bn less than 0 plus delta plus 0, which is delta, for sufficiently large n, or whenever n tends to infinity, we will have this inequality. And since the distance between an and bn is less than delta, we have the distance between their images f of an and f of bn less than epsilon for sufficiently large n. Since f of an converges to g of x and f of bn converges to g of x dash, we have the distance between the limit of this sequence x g of x and the limit of this sequence, which is g of x dash, is less than epsilon. Thus we have proved that g is uniformly continuous. Now to prove that g is unique, let us consider another function, say g dash from x to y, be another uniformly continuous extension of the function f. Then as g and g dash, both of them are extensions of f, g and g dash will agree on a, that is g of x will be equal to g dash of x for every x element of a. Now we need to show that g and g dash will agree on x minus a also, that is g of x equal to g dash of x for every x element of x minus a. To prove this, let x be an element of x minus a, then g of x is the limit of f of an, and as an belongs to capital A for every n, f of an is also equal to g dash of an, and as n tends to infinity, we know that this is equal to g dash of x as an tends to x. Thus g dash of x equal to g of x for every x element of x. So g dash equal to, thus we have proved that the extension g is unique, and this completes our proof.